Yeah, as she mentioned, I'm Tandra Biswas from University of Missouri. I'm a PhD student in Civil and Environmental Engineering Department. I'll be presenting my research on detection of 11-keto-testosterone hormone in aqueous samples by molecular imprinted photonic polymers. And this is a collaborative work between me, Federico Fuchs, Dr. Federico Fuchs, Dr. Sally Kassim, Dr. Chung-Ho Lin, and Dr. Maria Fidalgo. And this project was funded by USGS. Okay. So today I will be talking on my research by following this outline. First, I will introduce the topic, then I will explain the theory, then discuss methods, results, and finally conclusion. So endocrine disruptors, such as hormones and hormone mimicking compounds, have been a significant concern for as emerging water contaminants in recent years. So endocrine disruptors is a natural or synthetic chemical that can interfere with the endocrine system. It can prevent hormones to bind to the receptor, or it itself can bind to the receptor, which sends wrong signals to the body. The main sources of these chemicals can be pharmaceuticals, agricultural runoff, or industrial chemicals, wastewater treatment plants, and so on. Um, as they are present in the environment, they can cause many health hazards like hormonal imbalances, fertility issues, developmental abnormalities, and so forth. In fact, they can cause increased cancer risk, for example, breast, prostate, and thyroid. Their activity in very trace amount in the environment makes them a serious concern for both humans and wildlife. Therefore, it is crucial to monitor these chemicals in the environment. And for this reason, reliable detection is required. There are many traditional detection methods such as liquid chromatography, but this method is costly and time consuming. For keeping this in mind, by keeping this in mind, we developed a polymeric sensor using the molecular imprinting technology, which is cost efficient, fast, and easy to use. For this research, we have selected 11-keto-testosterone as our target analyte, which is an oxidized form of testosterone. It is a naturally occurring androgenic hormone, which is primarily found in teleost fish. In humans, it is the dominant bioactive androgen during the adrenarche and premature adrenarche in children. The basic theory of molecular imprinting is that first we prepare a polymer with the presence of the target analyte. Then we remove the target molecule from the polymer, which creates some cavities which are exactly complementary to the size of the target molecule. So when we expose the polymer in a solution containing the target, the molecules can directly fit in the cavities, and from there we can find the optical response to determine the sensor signal. We prepared the polymer inside a sacrificial photonic colloidal crystal, and by removing the colloidal crystal from the structure, we get the inverse opal photonic polymer, which is also a hydrogel. The detection is based on the reflectance mechanism of this photonic polymer, which follows the Bragg's diffraction law. The law says that when light encounters regularly spaced layers of particles and the diffracted waves are in phase, it creates an amplified signal like this, the graph, the spectra graph, which is shown in the right corner on the bottom. So when the polymer detects, when the polymer binds to the target molecule, the position of the peak of the spectrum shifts from the left to right. And then we find out how much shifting occurred to determine the sensor's signal. For fabricating the polymers, first we prepare a colloidal crystal deposition on a glass slide, the colloidal crystal from silicon nanoparticles. Then we prepare a pre-polymerization solution of acrylic acid containing the target analyte. And we conduct the polymerization inside the void spaces of the colloidal crystal under UV radiation. And after that, we remove the silica particles from the polymer, and in this stage, number F, in this stage, we get the inverse opal polymer. Finally, we wash away the target analyte from the polymer, and we get the molecular imprinted polymer. So, and the cavities are created, and we can use this for the hormone detection. By following the same procedure, we also prepared a non-imprinted polymer, which is the control of the study. For measuring the response, we incubate the sensors in the samples, then measure the reflectance using a UV visible spectrophotometer and get the response, which is shown in the right, and upon binding, it shifts from the left to right. For determining the performance, we prepared 9 samples, 9 hormone solutions, and the concentration starting from 0.1 ppb to 50 ppb. The first figure is showing the raw data collected from the spectrophotometer, where these are corresponding to the spectral shifts for different concentrations of the 11-kT hormone. The diffraction peak shift, the average diffraction peak shift and their standard deviation was plotted against the concentration. The extent of the shift increases with the degree of binding of the target to the imprinted sites. Excitingly, these MIPS, they could detect really low concentrations such as 0.1 ppb, and the maximum shifts was pronouncedly high, like 34 nanometer. And the limit of detection was 0.0 ppb and quantification 0.17 ppb. However, there was some shifts for the non-imprinted polymer, which is due to non-specific absorption. We also fitted the data in different isotherms, and Langmuir isotherm could explain the data better than Promlik. For determining the effect of ionic strength and natural organic matter, we incubated the MIPS in different salt solutions and containing also without and with natural organic matter. And it was observed that the matrix, the background matrix itself could induce some reflectance, and induce some spectral shifts, and there the divalent cations had the most effect. So normally calcium ions can significantly, they can pronouncedly change they can create conformational changes in the polymer structure by bridging effect, which makes the polymer contract or be rigid. And besides, calcium ions have high charge density, and they have strong hydration shell, which can change the surrounding water structure and ultimately influence polymer interaction. For evaluating the effect of ionic strength on target binding, we incubated the polymers in solutions containing sodium chloride and calcium chloride in the presence of target with different concentrations, 0.1 to 50 ppb, and found that from the first graph, their sodium ion is mildly suppressing the detection ability. However, it is not significantly changing the MIP performance. The maximum shift for both MIP in DI and sodium chloride are 34 nanometer. So it can be said that monovalent cations have less impact on the detection performance. However, on the other side, calcium is causing an underestimation. The reason behind this might be calcium, as I already explained, that calcium might cause rigidification of the polymer, which can make the analytes, they cannot pass through the polymer and the diffusion is low. That's why there is some underestimation we can see. And also I want to mention that there is some, with the increasing ionic strength, there was increasing non-specific absorption too, which might be a reason of salting out effect. And it was high in calcium chloride. We also incubated our sensors in DI-NOM, sodium chloride NOM, and calcium chloride NOM solutions. For this time, we rinsed all the MIPS after every incubation to reduce the surface fouling effect of NOM. So from the, by analyzing the first crop, it is also seen that in the presence of NOM, there is underestimation. So the reason behind this might be that the less availability of 11-KT molecule in the solution because of complex formation with the NOM. Similarly, for sodium chloride, there is no significant difference. Both of their detection for the maximum shifts are around 24 nanometers, so sodium does not have any effect in the presence of NOM2. But for calcium chloride solution, there was a significant drop in the performance. This is also the reason that there might be very less amount of target molecule present because of stronger complex formation. 11-KT molecule can be trapped inside calcium ion and NOM complex, so they might be less available. Besides, calcium has this effect of they can create the bridges between the polymer structure, and it can make the sensors rigid. So these are the reasons. These might be the reasons for the drop. So for this research, we to see how the sensors work in the presence of NOM and ionic strength, we use a significant high amount of ionic strength but this amount of salt is not typical in drinking water and natural waters. So that's why we saw this kind of underestimation. However, this effect can be lessened by, these issues can be lessened by using a calibration curve, which is specifically designed for the ionic strength and NOM of real waters, ensuring very high performance for these sensors in such samples. In conclusion, we can say that the developed molecularly imprinted polymer, it has demonstrated high efficiency in detecting 11 keto testosterone as low as 0.1 ppb. And these sensors are designed to be user-friendly, portable. It can be easily carried to the field and analyze any kind of environmental samples. Also, these sensors can provide a cost-effective and accessible alternate for the traditional HPLC analysis, making hormone detection more efficient, and it will encourage the monitoring of hormones in drinking water, natural waters, ultimately contributing to the reduction of exposure risks for both humans and wildlife. For our future work, we will test the sensors in the presence of analogous compounds, which are the similar kind of structure of 11-KT molecule. We will see how they perform. And finally, the MIPS will be applied for real life measurement. We will use these sensors for detecting 11-KT in fish physiological fluid samples. So we have also characterized the polymer and the depositions of the colloidal crystal, but for time shortage, I didn't show it. So yeah, that's it. Thank you.